So, time to get started. Yesterday's lab probably took, I assume that everybody spent the majority of their time drawing those phasor diagrams, right? Because you've done vector addition. It's just vector addition, but you haven't done this vector addition before. And so it takes a little time to figure out how you're doing the vector addition. Hopefully your answers were all pretty good this year because, we took care of the biggest problem. There are two people who didn't get the frequency data done, so you'll need to come in and do that. I won't be here on Thursday or Friday. Obviously, Friday's too late anyway. But I put the material up in the cupboard next to the lab station you were at, so you can come and do it. I will be here this afternoon from 1 to 5 if that works for you for finishing up that last section of the lab. Okay, we're starting a new section. This stuff here, well, actually, we're finishing what's going to be on the exam, I should say. It's a new chapter, chapter 24, which is the last chapter of the exam. It's a small portion of the exam because obviously we're covering it in one day. What it is a segue chapter. It's a chapter that connects what we've learned about electricity and magnetism to what we're going to be stepping into, which is optics, studying light. So the key for this chapter is in this one picture right here, which we're going to come to later, that light is an electromagnetic wave. So I'm going to come back to this picture and we'll discuss it more carefully when we get there. But first we'll start with James Clerk Maxwell. For whatever reason, it's really important to me that James Clerk Maxwell's father was born with the last name of Clerk. That the name Maxwell was an added name because his father inherited an estate from the Maxwell family. Why is that important to me? I don't know. So James Clerk Maxwell was looking at electricity and magnetism, and in his original work that he produced in 1855, he was able to take all of the different variables and calculations, equations that people had come up with electricity and magnetism, and he was able to combine these down. Combine things that really were the same thing, looking at it from a different angle, and say, all we really need is these 20 equations and these 20 variables, and we can explain everything in electricity and magnetism. So that was in 1855. By 1861, he had done more work, and he said, wow, you can even go smaller. You can get down to just 4 equations relating electric field, magnetic field, time, and position. And so now we have these 4 equations that he realized describe everything in electricity and magnetism. We call those collectively the Maxwell's equations. So the Maxwell's equations are not equations that James Clerk Maxwell developed. They're equations that he said, these are the ones that we need. All the others are just special case things. So something like Ohm's law is not one of the fundamental equations. It's a special case situation. Actually, I got the dates wrong. Darn it. He did his work in 1855. They published in 1861. I said that his second one was published in 1861. That was 1873 when he published the second one. Sorry, I got the dates wrong. The dates won't appear on a test, so that's not going to hurt you if you've memorized it wrong based on what I first said the first time. When he combined these equations, he realized that they predicted that you could have a wave sustained by electric and magnetic fields. Now, if you stop and think about it just for a little bit, it's a little confusing because when we talked about the electric field, when I introduced the electric field, I said the electric field is not something that's really there. It's a calculation to make it easier for us to calculate what the force is going to be on something. And likewise with the magnetic field, it's not the field that's physically present, it's the magnet that's present, and there's going to be a force due to that. But now, Clerk Maxwell has determined that these force fields can actually sustain a wave. And so we're going to look real briefly at how these equations predict that you can sustain a wave. So first, what are the 4 equations that you need to describe all of electricity and magnetism? And why didn't we just learn those 4 equations? Why did we have to learn all this other stuff? Well, we had to learn a little bit about how electricity and magnetism is going to affect us. So we had to learn some of the special cases. But the first one is Gauss's law. In the physics with calculus class, we learned Gauss's law. In the general physics version, we actually did not look at Gauss's law carefully. But Gauss's law, we did talk about its ramifications. Gauss's law says that the electric field coming out of a charge is proportional to how much charge you have. That's what Gauss's law says. The actual writing of it is that the electric flux going through a closed surface is equal to the charge enclosed divided by the permittivity of free space. So that's the first one. So it's one that we kind of talked about in general physics. In college physics, we definitely talked about. We talked about Coulomb's law in general physics a lot. Coulomb's law is fundamentally the same as Gauss's law. It's just looking at it from a different angle. So that's the kind of thing that Clerk Maxwell eliminated. We don't need two different equations that are looking at it from different angles. We only need one. The second law is Gauss's law for magnetism. I clearly mentioned Gauss's law for magnetism, and then we just moved on and didn't ever use it. Because Gauss's law for magnetism seems like a throwaway law. Gauss's law for magnetism says that the magnetic flux on a closed surface is equal to the permeability of free space times the magnetic charge enclosed. Well, tell me what you know about magnetic charge, because you're going to be tested on it a week from yesterday. Magnetic charge produces a current? We only really learned a couple of very basic things about magnetic charge. That we have north and south, and we have no monopoles. So that means anytime you have a north charge, you have a south charge with it. So what's the total charge always? Zero. So the total magnetic charge is going to be zero, hence Gauss's law for magnetism simplifies down to the total magnetic flux on any closed surface has to be zero. That is, the total magnetic field coming out and going in, added up, has to be zero because you have no net magnetic charge. The only other thing we learned about magnetic charge is that just like electric charge, opposites attract and likes repel. That's pretty much all we learned about magnetic charge. Then we have the last two, Faraday's Law. Well, we've just been working with Faraday's Law. We learned that the EMF induced is equal to minus n times the change in magnetic flux over change in time. In a general sense, you actually remove that n because that n was specific to number of coils. In a general sense, you just put that number of coils inside the calculation of the magnetic flux. So I took off the n just to give it the general sense. So that was Faraday's law. And then we have, it says Ampere Maxwell law. We've got the name Maxwell in a Maxwell equation. We had Ampere's law that said, and this is I think what Ashley was thinking, that if you have a moving current, it creates a magnetic field. Now remember, for the test, we have all kinds of right-hand rules now. We have the right-hand rule for cross product. That is, if A cross B is equal to C, then you take your right hand, make sure your index finger is perpendicular to thumb and straight. At A, the first thing to cross product is your index finger. Your middle finger should be able to bend to wherever B is, the second item in the cross product, and the thumb points to the answer, which in I said A cross B is C, so the thumb would point to C. That's one right-hand rule you need to have. Another one is if I have a current going through a wire, I put my thumb in the direction of the wire. So thumb in the direction of the wire, wrap my fingers around the wire, and if I want to know the direction the magnetic field due to that wire is at some location, I orient my hand so my fingertips are between the wire and the place I want to know the magnetic field, and the direction my fingertips are pointing is the direction of the magnetic field at that point. So the magnetic field is doing circles around the wire. That's the one that we need for Ampere's law. The third one we learned was if I have a loop of current, if I wrap my fingers in my right hand, the direction the current is going to loop, my thumb will point the direction of the magnetic field, the center of that loop. It'll come out of the center, go around the outside. That's just an application of the second one to a loop. So we have to know all of those right-hand rules for the test next week. So just making sure I review it now. Ampere's law was the law that said if I make a loop, that the circulation, the product of the magnetic field parallel to each piece of my loop as I go around the loop, is equal to mu naught, the permeability free space, times the current enclosed. That was Ampere's law. But Ampere's law had a hole in it that Maxwell realized. Maxwell said, okay, let's imagine that we have a parallel plate capacitor. And I mentioned this in class yesterday morning for, the calculus people. We have a parallel plate capacitor and we are charging it. We have current flowing into one side, flowing out of the other side. And using our right-hand rule, we'll have a magnetic field created by that current flowing to and flowing out of the capacitor. Any problems with that? Is that clear or is that nonsense? Oh, somebody said nonsense. Okay, Ampere's law said that if you have current going through a wire, it's going to make a magnetic field that goes around the wire using the right-hand rule. And so that should be making sense. If that's not making sense, then you'll want to review Ampere's law before the test. But then Maxwell says, well, what about between the plates? There's no current passing between the plates. So if I were to try to apply Ampere's law between the plates, I'd say no magnetic field. We don't actually need to do an experiment to test this because Ampere said, well, we could just take this loop here. So I'm going to take this loop right here. And instead of making the surface that we're looking for current going through right there, that's the obvious surface that any normal person would choose. We can instead make our surface so it goes like this. So I have a closed surface that's like a balloon that's been blown up. So the balloon is passing between the plates of the capacitor, and there's no current going through any piece of that balloon. Well, according to Ampere's law, the current enclosed is zero then, and so the magnetic field would be zero. So now Ampere's law would say it depends on where you choose to make your surface if you have a magnetic field or not. Well, that really is nonsense. That makes no sense. It can't depend on where you choose to make your surface what the magnetic field is at this location. Right? I can't just say, oh, I want to choose here, and boom, the magnetic field measurement goes to zero. I want to choose here, boom, it goes up. Right? My choice of where I want to make my calculation doesn't change the reality. And so Clerk Maxwell said there must be an equivalence to the building of the electric field in those plates. That is, the building of the electric field will create a magnetic field just like a current did. And so he went ahead and he calculated an equivalent current for a charging capacitor. So current, now this is a calculus version of the equation. The non-calculus version is current is equal to the change in charge over change in time. For a capacitor, Q is equal to CV. So that's the change in capacitance times voltage over the change in time. But then for a capacitor, I can put in my physical capacitance. So the physical capacitance is epsilon 0 A over L. And then the voltage, if I have parallel capacitor plates, the voltage difference between the plates, we've already learned V is equal to Ed is the way I said it in class. The voltage, if you have a uniform electric field, is the electric field multiplied by the separation or multiplied by the distance parallel. So replacing voltage with E times the separation of the plates. And then we have, well, what's constant? The emissivity of free space, or permittivity, of free space is constant. So the epsilon 0 is constant. The area of my capacitor plates is constant, assuming I just have a simple capacitor. The separation between the plates is constant. And so this simplifies to bringing out all the constants. Notice the L over L cancels. And we have that. Now, the way he actually does it is combines the way I have above, combines the area of the electric field to say the change in flux. So epsilon 0 times the change in flux over the change in time is an effective current for what's going on when you're having a change in electric field. And so Maxwell said we'd better add that in as another option for current. We could have an actual physical current, or we could have a changing electric field, creating what he termed a displacement current. And so if you put it together, you have, here's the normal current, and then here is that, quote, displacement current. And that's what makes it the Ampere Maxwell equation. You've got the additional displacement current. So here are the Ampere, or the Maxwell's equations, written out in two forms. These are both calculus forms, you'll notice. These equations are calculus equations. They are equations that you can work with much better with the calculus knowledge than you can without. Now, if you're in the Physics 152 class, you might say, oh no, am I missing out on something? Well, yes, you're missing out on a lot of hard problems, because these aren't easy problems, but they're problems you can do with calculus, whereas you can't do them without calculus. So we don't go over the things you can't do in this class. Okay, it's not a lot of point to say, well, here's another thing you'll never do. So we have these four equations. My students in my quantum class, I told them that the homework problem was not as easy as the problem we just worked out in class. They said my deadpan delivery was pretty funny, because it's obviously clear that the homework should be harder than what you did in class. Not always. Okay, so these equations, Clerk Maxwell combined these equations and showed that you can take these equations and predict electromagnetic waves. So physicists, being some of the funniest people on earth, love to walk around wearing one of these two variants of a shirt. This here is the differential form of the equations. Del dot E equal, of course, being an anal physicist makes life harder. Got to fix that. Del dot E is equal to 4 pi rho. Del cross E is equal to minus 1 over C dV dt. Del dot B equals 0. Del cross B equals 4 pi over C J vector plus 1 over C dE dt. Those are Maxwell's equations, and those predict an electromagnetic wave, of which light is an example. So God said, God made these laws, and there was light. Now, I'm going to step away from physics just for a minute and talk about something that's near and dear to my heart. I am a creationist. I believe that God created not only the universe, but life on this earth. And you have something like this. Often when the people wear this, they're actually kind of mocking our idea of God creating things. But to me, it's actually exactly what happened. I believe that God created the laws of nature, the laws of physics, as I like to call them, because physics is talking about nature. He created these laws, and he created these laws very carefully, I believe. Well, very carefully. I mean, he's God. I don't know how careful you have to be to do it right if you're God. But he created these very precise laws that govern how nature works and allows for us to have a universe that is sustained, not something that has disappeared in a few months, that allows for life to form. And so I believe that God made these laws so that we could have what we see as light. And he made the atmosphere so the atmosphere is transparent in the same range that our eyes can see, so we can see beyond the earth and see what's out there. Because imagine if God had made us with infrared vision. We wouldn't be able to see beyond the sky, we wouldn't see the stars out there. We might have by now figured out there were stars out there, but it would have taken much longer to realize they're there. I think God created us with all of these things in mind so that we can appreciate the world. So I view this and I say, yes, that's exactly what God did. He created these laws so that when he created us, we would be able to appreciate it, so we would have a lasting world. Okay, just had to get that off my chest. Here's the other version of the shirt. This one's with integral equations, and you can go either way. You can find them online. Yeah. Our first of the clicker questions. There are two right in a row here, and I think I figured out how to make it so we won't have problems with our clickers. We shall see. Okay, it's open now. How many equations are necessary to describe all of electromagnetism? Okay, waiting on Angelina and Corso. Don't have it?
No, I have it. It's not working.
It's just not working?
No, it's working.
Okay. Okay, everyone's answered. Thankfully, the answers got better over time. We had 18 that said 4. And we had 2 that said 20. In the interim, we had some other answers, but people moved away from them. I did mention the word 20, the number 20. But that was the number of equations from his work that he did in 1955. They published or 1855. They published in 1861. So 20 was what he thought when he thought he had really narrowed things down. But then in the end, 4 is the ultimate number. Those 4 equations, the 4 that we saw on the shirts. Now, how many of Maxwell's equations did James Clerk Maxwell create on his own? Okay, Erika and Angelina. All right. Okay, we had pretty good agreement here. Edward, lay some knowledge on us.
I chose part of work.
Why'd you choose that?
I don't really have a reason.
Okay. Anyone want to help him out? Alex?
Made a contribution to,
Yes, he modified Ampere's law. Made a contribution is probably a better term than modified. It's just shorter. Brandon?
That's my question. Doesn't that contradict what your question asks? It says on his own, so he moved part of one.
He.
That's not true.
That's what I put it on.
You okay? I'm happy. I'm not. There's no point in quibbling about the technicality because this is just for us to discuss it. Yeah. In my interpretation, I said that he created on his own part of Ampere's law, and so that's why I went with part of one. He clearly did not. One would clearly be wrong, right? And 2, well, 2 is more clearly wrong because he didn't get there. But he modified Ampere's law. That's the original work that he did, but combining them was also original work. It just wasn't coming up with the equation. It was saying, hey, this guy's law, this guy's law, this guy's law, this guy's law with this addition that I had to put in, that explains everything, which is pretty amazingly good work. Okay, now, what did he find from those equations? Well, we already know, and I'm going to go back to the equations here. We already know that if I have a charge moving, that will create a magnetic field. But with his modification of Ampere's law, a changing electric field will create a magnetic field. So Ampere's law now tells us that a changing electric field creates a magnetic field. And we had from Maxwell's, the Maxwell-Faraday equation shows here, from Faraday's law, that a changing magnetic field creates an electric field. And so by combining, and it actually requires combining all of these equations, I think. We did it yesterday. I think, I can't remember, apparently 24 hours ago. You combine these all, okay, we combined 3 of the 4. And you find that the electric field change with position, it's a second derivative, is proportional to the electric field change with time, again, a second derivative. So the electric field depends on the change in electric field is basically what it's saying. And so you sustain an electromagnetic wave. And if you have just charge moving at a constant speed, that's not going to create a changing magnetic field. That's a constant magnetic field. So the charge has to be moving at a changing speed to create a changing magnetic field, to create then electric field. So to make an electric field, you can't have to make an electromagnetic wave, you can't have static anything. I can't just have a pole and run current through that pole and make an electromagnetic wave. If I have a constant current running through this pole, what's it going to create? Constant current will create what? It will create a constant magnetic field that's going around it. But if I have a changing current, that changing current, which would be the result of a changing electric field, would produce a changing magnetic field, but the changing magnetic field will then induce an electric field, and the changing electric field that's induced would go back and forth. So you have to have change. So you have to have accelerating charge that's not going at constant speed, but that's accelerating to create an electromagnetic wave. So there is no such thing as, notice I didn't quite fit the last line on the slide, so I modified it by hand. There's no such thing as an electric wave. There's no such thing as a magnetic wave. You have to have electric and magnetic fields together to make a wave. So it's an electromagnetic wave, not electric wave, not a magnetic wave. Usually we just say EM waves. I almost wrote EM waves down there to save space where I wrote in red. So here's an example of creating an electromagnetic wave. What do we have here? What we have is a dipole, like let's say a water molecule. Water molecules are electric dipoles. And if that water molecule is rotating, then the charge is going up, down, up, down, up, down, up, down. And that's going to then create an electric field that would be pointing up, then pointing down, then pointing up, then pointing down as it oscillates. But at the same time, you have a current that's going up and down as the charge moves up and down. And that's going to create magnetic fields that go around it, perpendicular to the electric fields. And so you make electric fields and magnetic fields that are perpendicular to each other. And because the changing electric field will create a magnetic field, the changing magnetic field will create an electric field, you create electromagnetic waves that radiate outward. So you have them propagating like this. An important relationship. Electric field is equal to the velocity crossed with the magnetic field. We actually saw that a long time ago when we looked at having a charge that was balanced so it didn't accelerate, or you have electric field, magnetic fields crossed. That's a rule that holds for electromagnetic waves. What this means is V is perpendicular to E, right? And it's perpendicular to the magnetic field. And in fact, for an electromagnetic wave, each one of these has to be mutually perpendicular. So if I look at my picture, my electric field, let's simplify our picture. Let's say that we have electric fields that are purely vertical. That means our current is an infinitely long wire going up and down. So my electric field is purely vertical, an infinite wire. What direction is the magnetic field going to be? If it's a wire, magnetic fields can go around in circles. So I'm going to have the magnetic field in horizontal circles, the electric field vertical. What direction can the wave travel then if it's perpendicular to both of those? Perpendicular to vertical, perpendicular to, let's take this horizontal direction. If it's perpendicular to those two, what direction can it travel? That way. So the electric field, or the wave, can only travel in the situation I gave you. It can only travel out radially from the wire. It can't travel in an upward or downward direction. So the direction the wave propagates is restricted for an electromagnetic wave. Now we can talk about this picture more carefully. This is the picture that was on the opening slide. This is showing the relationship between electric field, magnetic field, and velocity. You'll notice C here. C is the velocity of an electromagnetic wave in a vacuum. If you're moving in something that's not a vacuum, it will always be slower than that. So if I have an electromagnetic wave traveling through the air, it's going to be slightly slower. A very small difference, but slightly slower. So remember that equation we just had, that E, and I'm just going to go back to it to make sure. I'm trusting that I had that equation right. E is equal to V cross B. So in this picture, I can test that. If I put E equals V cross B, how do I use the right-hand rule to confirm this? E is your thumb. V would be my index. And then B would be the magnetic field. So let's just check and make sure I have things right. So my thumb is E. My thumb goes like this. And then I need my index finger to be the direction of B. So like this. Right, row. I apparently have my equation with the sign wrong, right? Because if I have my thumb up, or wait, my thumb was electric field, and my index finger in the direction of V, which is that way, my middle finger points into the screen. So what that means is I had the sign wrong in that equation. That's why I tested it. So it must have a minus sign there because I know this figure is right. And I put that equation on there, and I started to worry about when I got to this because my recollection was, I think I had it backward. So you have this fixed relationship between the electric field, the magnetic field, and the direction of propagation. And I am sorry for having that equation wrong.
Why is it negative again?
Because to make the right-hand rule work out. I mean, that's not the reason. That's why I knew I had it wrong. The reason comes from if I have, well, actually, I'm not going to do it here because I haven't. What I was going to do is not actually the real reason. So I'm not going to do it because I'd have to go back to looking at Maxwell's equations and start from there, and I'm not prepared to do that. Do you have a question, Lauren?
Yeah. What's the velocity on the plate?
The velocity is the C arrow. And so because these are mutually perpendicular, the velocity is perpendicular to the electric field, is perpendicular to the magnetic field and electromagnetic wave. In magnitude, this equation gives us the electric field magnitude is equal to the velocity magnitude times the magnetic field magnitude. And so I'll just put max and max here. And we would have then the speed is just the electric field maximum over the magnetic field maximum, this equation right here. So the relationship between the electric field maximum and the magnetic field maximum is just the speed of light. You can always, if you know the electric field, you can calculate the magnetic field. If you know the magnetic field, you can calculate the electric field because of that relationship. Ashley's question.
So the negative sign is just for your direction.
Yes.
Is it arbitrary time?
No, it's not arbitrary. I apparently had it wrong the first time.
Okay.
I say apparently because I'm pretty sure I did the right hand rule right. It's, you know, something we can't apply. Yeah. Definitely did not do the right hand rule right when my science did not agree. So notice the electric field, magnetic field are proportional. So when the electric field is 0, the magnetic field is 0. When the electric field changes direction, the magnetic field changes direction. And so these waves, that picture is trying to show waves that have, well, the electric field is like this, magnetic field is like this, and then they're going like that, like that. That's what it's trying to show. My hands is probably not much better than looking at the picture, but the electric fields are all supposed to be vertical. The magnetic fields are all supposed to be horizontal, and then the wave is traveling in that direction. So important things, if it's in vacuum, the speed is the speed of light in vacuum. Something else is slower. For now, we're going to focus on vacuum. When we start next week with light, we, of course, will move into things that aren't vacuum. Antennas. Many of us, I forget, I am the only one here who grew up with the television that had an antenna sitting on it, the little rabbit ears. You grew up with the rabbit ears? All right, you man. Okay, a few other people. Those rabbit ears were the biggest pain in the behind. You want to watch this channel and you go over and you adjust them just right to get the channel. And then you want to watch a different channel and you have to change them. And of course, as the kid in the family, you're the one that has to go do all the changing. Dad's saying, no, higher, no, lower, no, turn it, rotate it. No, not that way. Experience?
The one outside, of course.
Outside, nice. So what's going on there? What's all the big deal? First of all, the simplest kind of antenna. Now this one here is for broadcasting, but an antenna that broadcasts is also an antenna that can receive. So the simplest kind of antenna here is an electric dipole antenna. You have something here that has a varying voltage, a sinusoidal voltage. And so when this side is positive and this side is negative, you're going to have current that is flowing like that. But since you have alternating voltages, it's going to be flowing up, then flowing down, then flowing up. And that's going to make electromagnetic waves that travel out radially. So if you are, let's say at camp meeting. I go to SoCal camp meeting every summer. It's a wonderful experience. You have this large campground, and you want to have a radio signal that broadcasts up and down the campground. Well, you don't want to go up into the sky, right? You want to keep it horizontal. They used to have a radio station there. They don't anymore. Low power just to broadcast to the campground. So you want that to be a vertical pole somewhere in the middle of the campground so that you have the signal going out horizontally to all the campers. You're not wasting energy going up into the sky. Likewise, as a child, when I went to my grandmother's house, the one whose funeral is Friday, they leased out part of their property for a radio station to put radio towers in there. Now, this radio station is in California Central Valley, and they want to broadcast up and down the Central Valley. So they had vertical tower that was working just like this, except for it has the earth at the bottom and it's just a single tower. But there wasn't just one tower in their yard. There were multiple towers. Why would they put multiple towers? That's exactly right, Ashley. You have California Central Valley is like this. Well, you don't want to waste a lot of energy sending your radio signal this way and this way. You're either, you're hitting mountains. That's not doing you much good to spend a lot of your energy hitting mountains. And so if you make your antennae one here and put them in phase, then you're going to have the biggest part of your signal is broadcast this way. And if your spacing is right, you have no signal being broadcast this way. And so by using multiple towers, they can shape how the signal is going to be broadcast. And so just like with sound, when we talked about physical beats, and if you have two speakers, as you walk around a room, if they're exactly in phase together, you're going to have places where it's louder and softer. That's what they were doing with their radio signal to make it so they can be directional about it and not waste energy broadcasting where there's no one to hear it. So that's a simple dipole transmitter. For my receiving antenna, the rabbit ears, from my understanding, ideally you'd have it like this, where this is parallel to the electric field. And this one here is perpendicular to the electric field. The perpendicular one is your ground plane. And then the vertical one, if the electric field is up, it's going to create a current going one direction. If the electric field is down, it creates a current going the other direction. So you're creating a current in that wire. And so you're comparing the current between the two wires for what you're picking up with the antenna. Now, this seems kind of silly because if I just walk around carrying a wire rod, I don't have a radio station I can listen to, right? What I'm going to have to do to listen to that radio station is to make something that will tune into the radio station and amplify it. So how do I make something that tunes into the radio station? Well, you saw that in lab yesterday. If you make a combination resistor, capacitor, inductor circuit, you can make it so at one frequency, it resonates. And so if you have a carrier signal at that frequency, it will oscillate with it. It's just like pushing on a swing at the same rate that the swing naturally swings, and you'll get a bigger current. And so by having your natural frequency match the natural of your circuit, match the natural frequency of the broadcaster, you can actually amplify that frequency. So it's possible to make a little radio that is just very simply a long wire for your antenna, and then have a little resonating circuit. And you don't even need a battery, if I remember right. So if you're on a desert island with nothing but wire and a magnet so you can make a speaker, you could make a speaker and make a little radio. So you know what? Gilligan's Island, all they really needed was a magnet and some wire. They had a compass, so they got the magnet covered. Yeah, that's a very weak magnet, by the way. But you can make magnets other ways, and they just need a source of wire. Strip it out of the ship, and boom, professor is on target. Okay, here's an example of the dipole receiver. If you have it at an angle that's not parallel to the electric field, you're still going to induce a current in the antenna, but not as big. So that's why the alignment makes a big difference. You want to be aligned. Now, most of us would say, okay, take my grandmother's case. That was a vertical antenna. I should probably have my antenna vertical to match it. There is a little bit of problem. The Earth's surface being curved and whatnot, the direction can be rotated some depending on where you are, and based on the topography as well. So that's why you can't just simply say, okay, make it vertical and make this one going out perpendicular to the direction and we should be good. It's not so simple. Not the only type of antenna. You can also make a magnetic dipole antenna. When I was going through my lecture preparing for today, I was like, I just covered the dipole antenna. That was an electric dipole. This is a magnetic dipole. Magnetic dipole antenna, we used to have something that looked like this with our antenna. That is a loop. These days, you generally have something that's like this and has a whole bunch of wraps, like 20 wraps of wire. That's also a loop. And we've learned now that if you have a changing magnetic flux, the magnetic field is going in and changing, then it's going to induce an EMF. The more loops you have, the higher the EMF that's going to be induced. And so that is going to pick up a signal by picking up the magnetic field oscillations, whereas the electric dipole picks up the radio signal by looking at the electric field oscillations. And now you come to, is there anyone here that's a ham radio operator? Yes, that's right. You're required to. I know from your class you didn't have to learn any of this theory, but if you are a serious ham radio operator, which some of them are, then you learn about all these different kinds of antennae. There's lots of different antennae specialized for different purposes. There are some ranges where you're better off with the magnetic dipole antenna. Some where you're better off with the electric dipole antenna. Depends on what frequency range you're looking at. Finally, and this is my last slide, which corresponds nicely with the clock, these electromagnetic waves have a large spectrum of frequencies. Now, those frequencies could go from 0 hertz up to an infinite hertz, right? That makes a lot of sense. You can have any frequency. But we classify them, low frequencies, we call radio. So radio waves are low frequencies or long wavelengths. And you can use the relationship between frequency, wavelength, and velocity that we've already learned. That is, that the velocity is the frequency multiplied by wavelength to convert between wavelength and frequency. So this graphic shows you both the wavelength and the frequency, because if you're in vacuum, there is a direct relationship. Speed is equal to wavelength times frequency. So very long wavelengths are radio waves. Notice we have AM and FM, different frequency ranges. On your AM dial, you're going from like 540, that's 540 kilohertz, up to 1,400 and some kilohertz, or 1.4 megahertz. The FM dial is a much higher frequency range. You're going from somewhere around 86 megahertz to somewhere around 107 megahertz. So the frequencies on the FM dial are somewhere around 100 times higher than the frequencies on the AM dial. There's some differences there. There's some reasons you might want one compared to the other. What is AM radio most commonly used for? For what? For talk radio. AM radio is most commonly used for talk radio. Why? Well, AM radio it takes less energy to throw your signal long distance. So it's cheaper to have a long range station in AM than FM. But with the AM station, you only have somewhere in the ballpark of 1 megahertz for your frequency. You have 100 times that for the FM. That means that the amount of information you can carry with an AM station is about 1/100th the amount of information you can carry with an FM station. So if you want high sound reproduction, high fidelity sound, you're going to do better with FM. But for talk, nobody cares about your high production, high quality reproduction of sound. They care about being able to understand clearly. So AM is better for talk, FM is better for music. Question answer.
So can you own a frequency?
Can you own a frequency? The government licenses frequencies. Many people would consider ownership, and other people would say, no, it's licensed, it's not ownership. That should have been a question on your ham radio license test.